So we could have calculated these. You all have the skills to calculate this probability distribution. So, once you've done that, and we didn't quite get there, but once it, Precious, if I could have you paying attention for right now. I know it's tempting, but, so once you've done that, what have you created? What is that?
A bell curve?
Bell curve. All right, a normal distribution. You have recreated the most important statistical discovery in this field. The standard normal distribution, a normal bell curve. Let me ask you a couple questions about this. Suppose I were to have you all go home tonight and do this experiment. Flip a coin 20 times, write down the number of times it comes up heads. So you're going to do that tonight. Flip a coin 20 times, write down how many heads you get. Some of you? But no. But suppose suppose I were. All right, you're going to write down your answer. You're going to get like 8. Danielle's going to get like 7. Christina's going to get 12. All right, and when you come back next week, suppose we were to graph the answers that you got, the results you came up with on a probability distribution. What do you think that probability distribution would look like? It would look a little bit like this, but it wouldn't look perfectly symmetrical like this, because there's only 15, 20 of you. What if instead we were to ask every single Mercy College student, I think there's like 11,000 Mercy College students, we were to ask them, can you go home, flip a coin 20 times, write down the number of heads you get, and then we were to graph those 11,000 points of data. It would pretty much look exactly like this. Law of large numbers. All right, another question I might ask. Suppose someone comes to you and says, you'll never guess what happened last night when I was flipping that coin. I got 16 out of 20 heads. What is the probability of that happening? 16 out of 20 heads.
Like 1%.
Very simple.
Just divide it.
Well,
0, 0, 1.
it's this, right? You can first just read the probability. Like, it's about, we'll say 0.5%. There's a 0.5% chance of that happening. All right, that person who flipped a coin and got 16 heads out of 20s, what percentile were they in? Were they in the top 1%? Were they in the top 10%? Were they in the bottom 5%?
Top 1.
Top 5.
Yeah, they're close to the top 1. They're actually in somewhere in the 99th percentile. You might say to that person, wow, you were in the 99th percentile. The chances of you getting that many heads are less than 1%. So what we'll find is this normal distribution has predictable qualities like this. So this we can calculate because we know the probability of getting heads or the probability of getting tails. Suppose instead we were graphing the data of, say, trees in a forest, the height of trees in a forest. So we were to measure 10,000 trees in a forest. We were to take the average height. The most common height would be this one, the one in the middle. Some of those trees would be a little bit taller. Some of those trees would be a little bit shorter. Some of those trees would be a lot taller. Some of those trees would be a lot shorter, and so on and so forth. Now I will tell you, a lot of natural phenomena have this normal distribution, have this pattern. The reason they have this pattern is because the probability associated with a tree being a little bit taller or a little bit shorter is something that equates to a 50-50 chance of flipping a heads or flipping a tails. One tree may have gotten a little bit more sunlight. One tree may have gotten a little bit more water as it ran through the canyon. One tree may have had genetics that weren't quite as good. It's certainly not as simple as a 50-50 coin flip, but there's probabilities associated with that. And if we have 10,000 trees in a forest and we measure the height of all of them, it's very likely we're going to get a perfectly symmetrical bell curve. And when we have a perfectly symmetrical bell curve, we'll find all we really need to know are two things. What is the mean? What is the average height of those trees? What is the average number of coin flips? And how disperse is this data? Is this bell curve tall and skinny, or is this bell curve short and fat? So we know those two things, and we know that this data forms into a normal distribution. We can make assumptions such as that tree is in the 99th percentile. Or we can say there's only a 6% chance of a tree being that tall. Those are the kind of things we can assume and we can calculate if we know that the distribution is normal and we know those two things. The mean, the center of the distribution, and how dispersed it is, whether it's short and fat or tall and skinny. Does that make sense? All right, no one's shaking their head no, so that's a good sign. All right, so normal distribution. Let's think about how we quantify this bell curve. And I want to point out, I mean, I know there was some frustration when we were doing the calculations, but you did kind of calculate that bell curve. We got a couple of the right answers here. We did, and we got a couple of the correct setups for answers. We didn't quite get all there, but you calculated this normal distribution. And once you've calculated it, there are certain things we can assume about it because it falls into a normal distribution. And so then we're going to talk about how we quantify a normal distribution. We'll talk about mean, medium, and mode, standard deviation. Standard deviation is just another way of saying short and fat or tall and skinny in terms of that bell curve. We're going to talk about z-scores, which is a standardized way of looking at data, and the assumptions we can make if we have a normal distribution. So first, let's talk about the mean, medium, and mode, and standard deviation. We call these three things measures of central tendency. Mean. What is the mean of a pool of data?
Average, right?
Mean is the average. That is correct. So what was the mean of that pool of data when we flipped a coin 20 times? What is the mean number of heads that came up? Assuming we had 10,000 Mercy College students do it. And we reported that data and we graphed it on a distribution. What is the?
10.
10 is correct. Exactly. Median. What is the median of a pool of data?
The middle.
The middle number. It would also be 10 again. Because that heads, that coin flip example fell into a normal distribution, the mean, medium, and mode are all the same. We'll talk for just 5 minutes about data that is skewed, where the mean, median, and mode are not the same, but that's just a brief conversation. So the median is the middle number. If we were to line up all the numbers, the middle one would be the median, and the mode is what?
Most common.
Most common. All right, for a normal distribution, these are the same. For a non-normal distribution, they don't necessarily have to be the same. Okay, let me just show you some of the notation when we're calculating the mean. If the data are from a population, the mean is denoted by this letter U, this funny looking U. We call it mu. Mu is equal to all the points of data added up divided by the total number of points of data. So if we're measuring heights of trees in a forest, say we have 49 trees in a forest. We add up all the heights of all 49 of those trees, divide by 49, that gives us the mean, mu. Large N is the number of the whole population. Make sense? If we're just using a sample, suppose we have 50,000 trees in the forest, and we're just taking a sample of, say, 35, and we want the mean of that sample data, we use this notation, x with a bar over it. You can call this x bar. You can also call this the sample mean. The sample mean is all 35 of those trees, their heights added up, divided by n, the sample size. Little n is the sample size.
That's 35.
Yep, that's 35. So mu, population size, x bar, sample size, sample size. X bar, sample mean, little n, sample size. We'll use this so many times you'll get used to it quickly. Okay, we're good on mean? Medium, as we said, is the middle number. I don't want to discuss that too much, just the middle number. You line them all up, the one in the middle. Mode is the most frequently occurring number. In a normal distribution, that is the same as the mean and the median. It doesn't necessarily have to be. Mode is the most occurring number, and it is the high point of that Bell distribution. So even if it's normal or non-normal, the highest point will be the mode. Okay. All right, so let's take a look at a couple quick examples of mean, median, and mode. Suppose I'm looking at the income in a certain town. And in this case, I know everyone's income in the entire town. And I know that the mean income is 60,000, median income is 60,000, the mode income is 60,000. If I were to graph that data, I would have income on the horizontal axis, and I would have frequency of that income on the vertical axis. And it would be a perfectly distributed, symmetric, normal distribution. The mean, median, and mode would all be 60,000, and I would have normally distributed data on either side of that. So that's one example. Suppose instead I were to look at a different town, and I were to find that the mean income were 80,000, the median income is 60,000, and the mode income is 60,000. What is going on in that town?
More people making more than 60,000?
More people making more than 60,000. Okay, so that, the way you said that is actually incorrect, and it's tricky, because the median number is 60,000. What does that mean by definition?
The middle.
Middle number. We have 50% making more, 50% making less. So we cannot say we have more people making more than 60,000. But what can we say?
Positively skewed.
We can say it's positively skewed, yes. What that means is there's something about the people who are making more than 60,000. It's not that there's more of them. It's that they make relatively more than their counterparts on the other side of the distribution. So the rich people are really rich, and the poor people are just, kind of poor. Proportionally, the rich people make a lot more. It could just be one person. It could be one really rich woman who lives in town, who pushes the data up, who pulls the mean up to 80,000. There's not more than one of her, but she positively skews the data. Does that make sense? All right. Opposite example. Mean income 45, median income 60, mode income 60. What's going on in that crazy town?
The poor people are really poor.
Yeah, the poor people are really poor, rich people are just kind of rich. Yeah, so maybe we have a section of unemployment, like people who make absolutely nothing. So, and we have normally just more of a normal pattern on the positive income side. So the poor people are really poor, rich people just kind of rich. All right, so that would give us an example of skewed data. I think I promised you 5 minutes discussion on non-normal distribution. So that's actually pretty much the only time we'll discuss non-normal distributions the rest of the class. The reason for that is because the normal distribution is really what gives us any power in statistics. If we can assume things are normally distributed, that's the only way we can make predictions. That's the only way we can say that our predictions have any validity. is by assuming that certain things are normal. And we'll take certain precautions, of course, we'll do good sampling, we'll use that assumption carefully. But in order to make any predictions at all, we need that assumption. So, let's get back to our discussion of normal distribution. Before we dive right into that, we've already talked a little bit about this. I want you to answer this question. What is the difference between these two symmetric frequency distributions? Take a look at this one, take a look at this one.
There's less dispersion on the right.
Yes, less dispersion on the right. So these two frequency distributions are both symmetrical, and I will tell you they are both normally distributed, but there's less dispersion here than there is here. Suppose maybe this is income in a town. This might be a factory where everyone works for the same factory, and they all make about the same amount of money. Maybe someone gets a promotion, someone's been there 20 years and gets a promotion. Maybe there's some entry-level people here, but everyone makes pretty much the same amount of money. Maybe this is a different town where we have all sorts of different types of folks. We have people who work in factories, we have people who are, Wall Street traders, something or another. We have a wider dispersion of the data. And if you remember earlier when we talked about, when I just introduced the normal distribution, I said we need to know two things about the dispersion of, two things about a distribution. One, what is the mean of it, what is the center of it, and two, the dispersion. So, we want to think about how we can quantify this dispersion. And we do it with a term called standard deviation. The most common way to measure the variation of the data is standard deviation. Approximately the average distance between the individual values of a data set and the center of the data set. So by the center of the data set, we mean the mean, the average, and standard deviation measures the approximate variation from each point of data from the mean. Let me give you an example. I'm going to go to the example or the formula. I'm going to go straight to the example before I show you the formula. I'm going to go ahead 2 slides. All right. Suppose we have 3 employees. Now I'm going to show you the formula. Sorry about that. It's fine. Okay. So, does everyone kind of understand what I mean by the average variation of each point of data from the mean of that data? Everyone kind of have an idea so far? Alright, so how we're going to calculate that, say we're measuring trees in a forest. I'm going to calculate the average height of the tree at 12 feet tall. I want to know, on average, how different is each tree? Is each tree about 3 inches difference? Is each tree about 1 foot of difference? Do I have a lot of variation in this forest, or a little bit of variation in this forest? And how I'm going to calculate that is with this standard deviation formula. This funny looking O, we call this sigma, also call this standard deviation. 2 steps. First step, I'm going to measure the mean. Remember this funny looking mu, that's the mean. Alright, and then I'm going to take each point of data, each tree in this forest, and I'm going to measure the difference. So the tree in the forest minus the average. So this tree is 14 feet tall, the average is 12 feet tall. That's a difference of 2. Now the thing is, I don't care so much if it's a positive or negative difference. So I want just the absolute difference. This could be 9, and then the average would be 12, that would be negative 3, right? Alright, so it's either going to be a positive or negative number here. I don't care if it's positive or negative, so I'm going to square it. And I'm ultimately going to take the square root of that, but I'm going to start by squaring it to signify that I don't care if it's a positive or negative difference. So for each tree, I take the difference between that tree and the average. I square that. I divide by the total number of trees. And then if you remember, because I squared this at the beginning, I take the square root of that whole mess. And that's going to give me standard deviation. That make sense? All right.
Just for that one tree?
This sum, this big E, that's the sum of all those trees. So all the x's. And this xi, that means the first tree all the way up to however many trees I'm measuring. All right. So this is the whole population standard deviation. Suppose instead I don't want to measure every single tree. I want to take a sample of 35 trees. Then I'm going to get a sample standard deviation. I would use little s to signify that I just took a sample. I would calculate it in a very similar fashion. Remember, when I take a sample, I get this x bar, sample mean. All right, I take the difference between each tree in my sample and the sample mean. I square it. I divide by little n, which is the sample size. I make a small adjustment. I subtract n by 1. By taking n minus 1 in the denominator, I make this whole number a little bit bigger. So a smaller number in the denominator makes the whole number just a little bit bigger, to account for the fact that I don't have all the trees measured in the forest, I just have a sample. So I make my standard deviation just a little bit bigger, and we'll find that that just makes us, allows us to make a less precise statement. Don't need to worry too much about that for right now, just imagine that being less precise. And then I take the square root of that whole chunk and I get the sample standard deviation. All right, kind of make sense? Okay, I see some sort of nods. So now let me go to the example. All right, suppose you had 3 employees producing widgets. Over the course of one day, they were able to produce 3, 6, and 7 widgets respectively. So I have 3 employees. All right, you 3 are my employees. Danielle produces 3 widgets. Kristen produces 6 widgets. And Julissa produces 7 widgets. What is the population standard deviation of widgets produced? What's the first thing I need to do to calculate standard deviation?
Mean.
Mean, yes. All right. So 3 plus 6 plus 7 divided by 3 equals 5.3. I take the difference between the number Danielle produced and the mean, square it. The difference between the number Kristen produced and the mean, square it. The difference between the number Julissa produced and the mean, square it. Divide that whole thing by 3, take the square root of that. I come out with 1.7 widgets as my standard deviation. So the mean is 5.3. And 1.7 is about the average distance of each of their number of widgets from the mean. And that's about right, because 1.7, the difference between 1.7, or the difference between, let's see, the amount Julissa produced and 5.3 is pretty much 1.7. The difference between 5.3 and 7 is 1.7. The difference between the amount Danielle produced, 3 and 5.3, that's 2.3. So that's a little bit more than 1.7. But then the amount Kristen produced is only 0.7 difference from the mean. So it's about 1.7 difference is the standard deviation of the widgets they produce. All right, and does that make sense? All right, sorry if I'm trying to rush through here. I want to get through this. I want to try to go fast so I don't lose your focus. But if I go too fast, tell me I'm going too fast. Suppose instead that these 3 employees were just a sample out of 10,000 employees. And I want to calculate the sample standard deviation of these 3 employees. I do it in a very similar fashion, except I divide by n minus 1, which is 2. And because I divide by a smaller number, I get a slightly bigger standard deviation. I take a larger number to account for the fact that I didn't sample everyone. I make a less precise estimate. So my standard deviation, if this were just a sample, would be 2.08. Does that make sense? All right. So, that brings us back to our normal distribution. We know two things. We know the mean of this distribution, and we know the standard deviation of this distribution. I also know, because this is normally distributed data, that the percentage of data within a given number of standard deviations is predictable. That is predictable because when I measure trees in my forest, and I plot those on a frequency distribution, and I calculate the standard deviation, and someone else in China measures trees in their forest, and they plot the distribution, they calculate the mean, they calculate the standard deviation, their curve looks exactly the same as my curve. And we call each other on the phone, and we're like, really? You have the exact same curve you're typing? That's like crazy, isn't it? The reason that happens, it has to do with the coin flip example that we did. And I talked about the probability of a coin coming up heads one or two more times can be equated to the probability of a tree getting a little more sunlight, a little more water, and over large numbers. And as long as there's nothing going on in this forest that is skewing the data, like we looked at a couple examples of skewed data with those funny towns of rich people and poor people and all that, as long as it's just completely random, my forest is going to look exactly the same as the person in China's forest. And I'm going to know how many of my trees are going to be within 1 standard deviation, 2 standard deviations, 3 standard deviations of the mean. I'm going to know exactly how these curves break. My curve is going to break exactly the same way as the guy in China's curve is going to break. Law of large numbers, normal distribution is a natural phenomenon. 3 of the things we know. 1, approximately 68.38% of the values in the normal distribution will be within 1 standard deviation of the mean. So 68.3 of my trees will be within 1 standard deviation of my mean. Just like 68.3% of the guy in China's, his trees will be within 1 standard deviation of the mean he calculates. 95.5% of the values will be within 2 standard deviations of the mean. 99.7% of the values will be within 3 standard deviations of the mean. These are just a few of the things we know. I could tell you exactly what percentage of the data would be within 1.78%, or 1.78 standard deviations of the mean. Because I can calculate every single thing about how this curve breaks the same way you all started to calculate that binomial distribution with the coin flip example. All right. So, what does this mean? Well, the guy in China, his trees may have a different standard deviation than me, and he may have a different mean, a different average height than me. But we can put his trees and my trees on the same frequency distribution. We can say that we're going to standardize it. My trees and your trees, we're going to call whatever mean we get of 0, and we're going to call whatever standard deviation we get, we're going to call it 1. And if he does that with his trees, I do that with my trees, our bell curves are going to look exactly the same, and we can both talk to each other on the phone about the probability of one tree being 2.7 standard deviations above the mean. We'll be like, wow, what's the probability of that happening? And we'll both calculate it the same way. And when we put things on a normal distribution, we give them a z-score. And a z-score is just the number of standard deviations above or below the mean. So if the average tree size is 16 feet, and the standard deviation is 1 foot. And I have a tree that is 18 feet tall. Okay, you with me? The mean is 16, the standard deviation is 1. I find a tree that's 18 feet tall. How many standard deviations is that tree above the mean? All right, mean, mu equals 16. Standard deviation equals 1. My particular tree equals 18. How many standard deviations is that particular tree above the mean? 2 standard deviations above the mean. That make sense, everyone? So we would take 18 minus 16 divided by 1 equals 2, divided by 1 equals 2. That's how many standard deviations that tree is above the mean. I would assign that tree a z-score of 2.
So. No, your M will, that will be an M, but it's not.
Oh, an M, sorry. All right. Okay. Okay. So that's z-scores. Z-scores. All right. All right, in my example, I had a tree size of 18. I had an average tree height of 16. I had a standard deviation of 1. I had a z-score of 2. All right, it can be above or below the mean. All right, now, I can do, suppose these are not whole numbers. Suppose I were to tell you I have a tree that has a z-score of 1.2. And I'm going to ask you, what is the probability of having a tree that tall? That has a z-score of 1.2. Well, what you're going to do is not only are you going to do that binomial calculation, but you're going to do every single number in between, all the decimal points. Someone else is going to do it for you, and they're going to put all that information in a z-table. And you'll have a z-table in the back of your book, and it will tell you the probability associated with any particular z-score. There's also a z-table in the back of your slides, and there's also a z-table, partial z-table, in the very next slide. So if I were to tell you what's the probability of having a z-score of 1.2, you would flip back to the z-table in the back of your book, and you would look how it works. Does anyone have, if you have your book with you, maybe you can open to the z-table. If you don't have your book with you, just look at on the back. Yeah, look there. It's fine. Look either one. Back or the slides. All right. How the z-table works is you will look down the vertical column for a z-score of 1.2. If it's 1.2, say if it's 1.27, then you would go 1.2 and you would go all the way across here to 0.7. So this is 1.27. What we're looking for right now is just 1.2. We will look for the area associated with that z-score. This is area under the curve. All right, and this tells us, this 0.8849, what this tells us is the area, the probability of having a z-score of 1.2 or less. .2 or less is 88.49%. We can tell that by looking at the z-table. Now, how did they come up with the z-table? They did something a lot more complicated than what you started to do with the binomial coin flip example, but not that much more complicated. You pretty much started to do the calculations that they did, except they just did a lot more of them. So does that make sense? Z-score of 1.2, what's the probability of having a tree that tall? Or you might say it a different way. You might say, what's the probability of randomly selecting any tree and have it being shorter than that particular tree?
Like 88%.
88.5%. What's the probability of a randomly selected tree being taller than that particular tree? About 12%, 11.5%. Does that make sense? All right. Okay. Great. All right, I want to do this example. Maybe you'll recognize it from Turbo. It just can put this in context for us. Suppose we have some data on male height. Suppose we know that the average height for an American male is 70 inches and the standard deviation is 3.5 inches. And we are able to assume that the standard deviation is normal. Assume that the standard distribution is normal. Assume that the distribution is normal. I wrote that wrong. So we assume that the distribution is normal. Okay. Suppose further, we know that Michael Jordan's height is 78 inches. What is the z-score that represents Michael Jordan's height? Fire away. All right, how do we calculate this? Z-score for Michael Jordan. Anybody?
2.29.
That's, how much? 2.29? Yeah, that sounds right. You say 2.29? Yeah. All right, but what are the numbers we use?
78 minus
78 is his height, minus the average of 70, divided by standard deviation 3.5, equals 2.29. Excellent. So Michael Jordan has a z-score of 2.29. All right, are we good there? Excellent. What is the probability that a randomly selected American male will be shorter than Michael Jordan? Keep in mind, we get to assume that this distribution is normal. Assume that it follows all those normal patterns. There's nothing skewing this data. What's the probability that randomly selected?
97%.
How much?
97.
Sounds.
99.
I like that one better. 99. How'd you get 97? You just guessed? Okay, so what we do is we look on the z table, and we look for a z-score of 2.29. And what do we see when we look under 2.29? 0.98?
Yeah.
So, all right, so that's more exact, 0.98 what? How much? Oh, 0.989. So we'll say almost 0.99. So 99% of the data is less extreme than that. 99% of males have a z-score of less than 2.29. So the next male who walks by that door, the chances of that person being shorter than Michael Jordan, 99%. The chances of that male being taller than Michael Jordan, 1%. Excellent. Okay, suppose Isaiah Thomas has a height of 69 inches. What is the z-score for his height? Fire away. All right, what do we get for a z-score for Isaiah Thomas? Say it loud.
It's negative 0.29.
That sounds about right to me. You like that? Okay, so it's negative, which means Isaiah Thomas is shorter than the mean, and he's about 3/10 of one standard deviation below the mean. All right, so we have a z-score for Isaiah Thomas. Right? We're good. What is the probability the randomly selected male will be shorter than Isaiah Thomas? Just give me the percent.
61.
61.
All right, so I think that's wrong. The reason that's wrong is because you'll notice that the z-table on the back of your slides does not have negative numbers. So you will need to make an adjustment.
Subtracted from 1.
Subtracted from 1.
30%.
Yeah. So what it's giving you is positive 0.29 is giving you what? 60 what percent?
61.
Yeah, so 61%. So this part here is 61%. All right. Thankfully, we know that the normal distribution is symmetrical, and it's identical on the positive and negative side. So what that means is, if this were positive 0.29, this would be 39%. Right? And if it were negative 0.29, we could just flip those around. So probability randomly selected male is shorter than Isaiah Thomas is 39%. 99%. Okay, we're good there? All right, I realize I'm throwing a lot of stuff here at the end of class, but there'll be plenty of time to absorb this. What is the probability a randomly selected American male will have a height in between Isaiah Thomas and Michael Jordan? How do we figure that out? Subtract the two? Yeah? Alright, so let's make this clean here. Alright, so this is a frequency distribution for male height. It's normally distributed. We know that Michael Jordan, all right, the chances of, let's see, how do we do this? All right, let's do it this way. We'll call this Michael Jordan. What's the probability of a male being taller than Michael Jordan?
1%.
1%, okay? This is 1%. All right, what's the probability of a randomly selected male being shorter than Isaiah Thomas?
39.
39%. All right, so we've got this part is 39%. This part is 1%. What's the part in the middle?
60.
Fantastic. Does this make sense? Okay, you should be very proud of yourself if you've got that, because I threw a lot of that at you fast. We're going to do one more example. If you want to, you can always go home, I guess. But I recommend you do this last example so we can just kind of ingrain this. Suppose driving distance for work for residents of a certain community has a mean of 21 miles and a standard deviation of 3.6 miles. What is the probability that an individual drives between 19 and 26 miles to work? Assume that the distribution is normal. All right, so we've got a mean, 21. We've got a standard deviation, 3.6. We want to know the probability between 19 and 26. How are we going to attack this?
Just do every single one.
The same way.
Not every single one, but just two, right? We need a z-score for this, a z-score for this, and we need some add, subtract, this junk here, right? So, does that make sense? Yeah? Okay, go. Let me make some room. right, what do we get for the z-score for 19?
Negative 0.55.
0.55, I like it. And what do we get for the z-score for 26? 1.388. All right, so let's draw a normally distributed commuting distance to work. All right, and we need to know the area between 19 and 26. All right, so we know the mean here, the mean is 21. All right, use pink here for 19. All right, so this is 19. This is 21. And then in a minute, we're going to need to find the z-score for 26. 26. Okay, so what is the probability of less than 19? Let's do it like that. We can do this in a number of different ways.
What's the third one? That's 25?
This is 19, 21, and 26. All right, let's do this. Let's do less than 19. What do we have there? So we look for a z-score of 0.55 on your z-table. 1 minus that is this area here. How much?
29.
29%? All right, this is 29%. Boom, 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 boom. All right. Now, how about the z-score associated with 26 miles? That's 1.388. And when we look up 1.388 on the z-table, what do we get? 93? All right, so I think it makes the most sense to calculate what we have over here in this part. So if we have 93 below 26, what do we have above 26? 7, okay. 7%. All right, and what's the question that we need to solve?
Between 19 and 26? So
Yes.
it's
Alright.
29 plus 7 is 36, 36 minus 100.
Yeah, and what do we get, Danielle?
64%.
64% is the answer to our question? Is that right? Okay. You survived. You feeling kind of okay with that?
Can you go over the negative one more time, please?
The negative?
Yeah.
Okay, so we looked up 0.55, and what did we get when we saw that on the z-table?
So 71, basically.
We saw 71. All right, so what that means, if we have a positive 71, or positive 0.55, 71% of the data would be to the left of that. All right, and because, which would mean that 29% would be to the right. So if it's negative 0.55, we know it's just reversed. That 29% would be below it, 71% would be above it. So we know that this piece below 19 is 29%. And for the 1.3, we don't need to do that reverse because it's a positive 1.38. We look it up. Actually, we do. We do because we wanted to calculate the amount above. When we looked up at 1.3 on the z-table, it said 0.93 something something. And we knew that that meant there was 7% above, which left a total of 64% in the middle. So the answer to the question, what is the probability an individual drives between 19 and 26 miles to work? 64%. So if you were to walk up to someone in a party at that town and you were to say, hey, I bet you drive between 19 and 26 miles to get to work each day. What are the chances that you would be correct? 64%. All right, great. You should be proud of yourselves. You made it through a lot of material to get us started. For the quiz, I think there's a combination question. There's a binomial distribution question. set up the number of combinations, number of successes, probability of successes. There's a question, I think just like this. I forget what else there is. Nothing that would surprise you. Best way to prepare for it, go over the notes for tonight, do the homework exercises, work the Excel a little bit, see if that helps you with the calculations. You may want to use Excel for the quiz. You may be more comfortable using the calculator after you practice with it for a little bit. Question?
Oh, it's not for that.
No, from, okay. All right, I'll be here if anyone has any questions. Otherwise, I look forward to seeing you next week. Thank you. Good job, Kristen. I know you're getting a little tired. Just stay focused.
You do know 1.3 on this.
Okay.
So the quiz is like this.
The quiz is before.
Yes. Well, it's 1.38. So 1.38.
I know she's teaching.
Yeah, and
I gotta go over the things I missed here.
Yeah.
Sorry about that. Yeah, 0.55 is gonna be about 71%.
I'm just
And
thinking
that
about
one's
the.
right, so 29% on the other side.
No.
So you know that there's 71% lower than that,
So,
if it's positive. Which means if it's negative, then it's one
this is
minus
like very long.
that means that there's 29% lower. What's your name again? Kyle. Okay. Worked out. Which is exactly.
A little concerned about how we
Yeah, I didn't get a chance to.
Okay.
last night.
Okay.
They just
Okay,
come
tomorrow, I
Thursday,
mean, Wednesday when I
Friday,
come back,
Friday.
I'll try to go
Yeah,
early.
yeah, yeah. Just don't worry about it.
Yeah, we'll be here
The first week
Yeah,
is fine.
Wednesday I'm
Just,
doing,
I'm sure I'll be able to get it done.
yes.
We are.
And then Thursday I'm doing, yeah,
Okay.
so I kind of broke up.
Okay, I mean, don't feel rushed. I mean,
And then you
stay
do
friends
business,
with class.
business.
Yeah, no, I was.
Government.
The government,
If you need, yeah, I
that
mean,
shouldn't
like I
be
said, it
that
doesn't come in
bad.
time.
I had signed up
Don't
for
worry,
that
I
too,
can-
and I
I'll shoot
just,
an email.
that's the
Okay,
way
all right. Have a good night. Good night.
I missed the first part of the short.
Oh, sure.
So, I heard quiz, I get nervous.
Oh, right.
So, all right, so,
That was great. What's your name
this
again?
Maury.
Maury. Got it.
So, we have a, I'm having like a real office. Granted, so basically,
Here, all right. You're not on Blackboard yet? Okay, yeah, so go to mercy.edu, use your credentials to sign into Blackboard. Once you do, we'll see.
I'll see you Wednesday.
We'll see a setup like this. You'll go to everything's under course material. To take the quiz. So first, all right, you have the textbook?
Not yet.
Okay. Okay, good. And I was just telling one of your classmates, you do it at a time, you don't have to do the quiz before next week. Just want to get it as soon as possible, so you don't get behind the class.
If you don't have.
Or you can make friends with someone in the class, is another possibility.
That's what he says, right? You wanna get it over.
Okay.
No, I wanna get it over, yeah, I gotta, for some things, so it's understands again.
Yes.
It's gonna come by,
Wait, no, you said the quiz is
You know.
when did you say the
it's
quiz?
due by the 5th.
Due by the-
So,
Okay, so once you get the book, if you look at chapter 2, you do exercise 1, 2, chapter 4, exercise 1, you do all these exercises. These are recommended practice that we recommend all the quiz. And then you'll do the Excel exercises at the end of chapter 2, this one, and chapter 5, this one, and chapter 6, this one. For the Excel exercises.
Oh,
I've
you're
got a bunch of Excel
very
exercises
comfortable.
here.
Yeah.
Click on that. Go click on the first one. This one. Up. Alright, boom, and these are all laid out. So this is chapter 2, exercise 1. Actually, I did this earlier for the rest of the students. You'll just fill in these parts. The textbook will explain exactly how you do it.
Okay.
For the mean, it's just need to use Excel, you know Excel.
A little bit.
So equals average, open parentheses, select all these numbers,
That's how he's doing the calculation.
close parentheses, boom, all right, 35, and you'll just do all of those, and then you'll go on to number 2, and you'll do whatever else you do there, very same thing, chapter 5, binomial probabilities, all that. Okay, so that should reinforce it a little bit, the exercises will be very similar to the quizzes. Then, when you're feeling all good and confident, you'll go to course material, you go to class quizzes,
But here's my,
you go to class quiz 1, open book, open note, we can do it individually, time limit 1 hour, 30 minutes, as soon as you start, you have to do it all in one sitting. Click begin, there'll be 5 questions, like you went over class, like we did, put in the answers. No need to show your work, partial credit is not given, highlight your answers in bold. Okay, so that's it. What else do we have? Did you have a quick question by any chance?
We're just watching this, which is
Oh, good.
good, yeah.
Following.
Yeah.
Following,
Good, good,
yeah.
excellent, excellent.
If
All right.
there's a question.
yeah. I know I'm gonna forget like.
So we know class quizzes, we already opened up the Excel exercise data, we filled in all those answers. Once we fill in all the answers and we save it, we're ready to submit, we go to class assignments. Click on that, click submit the first one. Now you know you need to submit the first one because you'll look on the syllabus and it'll say before December 5th
Right.
at 6:29 p.m. Take class 1 quiz and submit these Excel exercises. You'll upload something, I guess browse your computer, wherever you saved it on submit class 1 slides, whatever. Click submit, boom, you're done. Okay, what else do we have? I mentioned that a great technique to prepare for class is to look at the class slides. I will have these class slides up by Friday at the latest usually.
Okay.
I think this is easier than reading the chapter. So you can just look over the slides, know what we're gonna talk about in class, it will direct you with certain things. Then you can read the chapter to kind of fill in, maybe attempt a couple homework exercises before class, I think it's just a better way to absorb the data. Okay, so that's class slides. And class video recordings.
Okay.
Yeah, and you can,
Listen back.
yeah, you can listen back. We're being recorded right now, actually. Okay, and one thing I forgot to mention, once you take the class quizzes, you can look at the correct answers. Like all the correct answers will
Oh,
pop up,
okay.
and then you can look back at the correct answers. You do that by going to My Grades. All your quizzes and assignments will be here. You'll click on the class 1 quiz. Then you'll click on either the score you got or this little bubble that says needs grading.
Okay.
And once you click on that, it'll give you all the answers. Do a score. This is all the answers. Don't look, don't look, don't look, don't look.
Close my eyes.
Okay, oh, actually, it's on the video. You just go back, you scroll, you slow it down.
Pause, right?
Oh, boy. Yeah.
How many questions are each quiz?
Yeah.
This first one is 5 plus 1 extra credit.
Okay, so for each quiz, typically, the average amount of questions is like 5 for each quiz?
Yeah, yeah.
So if you get 2 wrong, that's bad.
I guess so. I have made an effort to make the quizzes more grade friendly. So I've taken out problem questions from last time, and I put an extra credit question in.
Okay.
So, yeah.